Good afternoon, and welcome to the Recreation Center Energy Efficiency webinar. Thanks for joining the webinar. My name is Cody David, and I'm a project engineer on the Commercial Sustainability Services team here at Southface Energy Institute. My background is in mechanical engineering, specifically commercial HVAC and building science. At Southface, I work with both new and existing commercial buildings, performing energy audits, energy modeling, trainings, program management, and data analysis. I've performed energy and water assessments for a diverse array of commercial buildings, ranging from high-rise office buildings and hospitals to small nonprofit shelters and community centers. Here at Southface, I also help to manage Southface's high-performance facilities. Our main campus has a current Energy Star score of 96, and the Eco Office alone has an Energy Star score of 98. This is an image of the Southface main campus. So Southface, we're a nonprofit organization, and Southface promotes sustainable homes, workplaces, and communities through education, research, advocacy, and technical assistance. Southface is located here in Atlanta, and we've been around since 1978. The building on your left is Southface Resource Center, and this building was constructed in 1996, and it's meant to be a showcase residential building. The building on the right is the Southface Eco Office. This is a LEED Platinum facility. It's meant to be a showcase commercial building and research laboratory. Got a green roof, PV array, passive solar design, and lots of really neat features. The Southface Eco Office is designed to consume 50% less energy than the typical office building and 84% less water. And we actually have a 98 Energy Star score, so we seem to be meeting those, or actually exceeding those goals. And this is the Southface Suite Center, and SWEET stands for Southeast Weatherization and Energy Efficiency Training Center. And this is an adaptive reuse project completed in October 2010. This building is certified using our own Earthcraft Light Commercial certification, and is also a LEED Commercial Interiors certified space. The facility serves as a green building training facility, and we've provided training for more than 3,000 building professionals to date. So today, we're going to cover the following objectives. First, what is energy benchmarking, and how can it support improving the energy efficiency of a recreation center? Then we're going to go over a pathway to 20% energy savings at a typical recreation center, followed by low and no cost measures that can be implemented today to save money. We'll also go over efficiency measures for properties with an indoor and outdoor pool. So first, we're going to go over a little bit about small commercial buildings and the Advanced Commercial Buildings Initiative grant. So small commercial buildings are defined as commercial buildings less than 50,000 square feet. When we look at the commercial building stock, it's dominated by small commercial buildings. They're everywhere. By building quantity, 94% of buildings in the commercial building stock are small. And on the basis of floor area, 49% of commercial floor area is also small commercial. In other words, nearly half of the commercial floor space is small commercial. The small commercial building stock is extremely diverse, representing nearly every property type and ownership class. It includes convenience stores, small businesses, restaurants, schools, higher education, municipal government, really just about everything. Historically, large buildings have been the primary target for energy service companies and efficiency efforts, while small commercial buildings have been overlooked. However, 45% of energy consumed by commercial buildings occurs in small buildings. Small commercial buildings have significant potential for energy savings, but there are formidable barriers that must be overcome using better tools, new technology, streamlined protocols, effective education, and proven solutions. And so we get to the Advanced Commercial Buildings Initiative. So Southface has a proven track record of improving the efficiency of small commercial buildings through several building efficiency programs, including Grants to Green, the nonprofit Energy and Water Initiative, and Earthcraft Light Commercial. Grants to Green is an assessment and retrofit implementation program that serves local Atlanta nonprofits. The nonprofit Energy and Water Efficiency Initiative is also an assessment and implementation program modeled after Grants to Green, but it targets Boys and Girls Clubs and Feeding America tool banks, first in the Southeast and now expanding throughout the country. Earthcraft Light Commercial is a green building certification program for new construction and major innovation that focuses on small commercial buildings. We've also worked with the City of Atlanta Loan Fund for efficiency improvements in municipal facilities. Finally, some of the buildings participating, or some of the buildings analyzed for the Advanced Commercial Buildings Initiative. So through working with these small commercial buildings through multiple different programs, Southface received a grant from the Department of Energy and other key partners. And this 3-year research-driven grant is called the Advanced Commercial Building Initiative. The goal is to remove barriers to resource efficiency in the small commercial sector. The Advanced Commercial Building Initiative enables Southface and its partners to develop research-driven protocols for building type-specific solution packages for both existing buildings and new construction that meet the required energy reduction targets. And those targets are 20% in existing buildings and 50% in new construction compared again back to 2003. We'll also develop data collection, analysis, and feedback tools to assist facility staff, building owners, and energy efficiency program managers to reach those savings goals, along with education and training and innovative approaches that overcome market barriers for financing and program delivery in the challenging small commercial building segment. So the grant is made up of 3 stages: research, demonstration, and deployment. In order to understand how small commercial buildings work and how to improve their efficiency, we first need to conduct research. So our research phase included work with Georgia Tech, Oak Ridge National Labs, and buildings involved in Southface's building efficiency programs. We analyzed building performance data and benchmarking data. We also installed circuit-level electricity monitoring sensors and other sensors in 12 buildings, collecting detailed data on energy consumption, water efficiency, mechanical systems, the building envelope, human behavior, lighting strategies, common appliances, and various other elements of small commercial buildings. This data was used in order to understand how existing buildings consume energy, in addition to evaluating the impact of energy conservation measures. Our energy efficiency strategies were tested and demonstrated in our existing building programs. And so that's the demonstration phase. So working with our partners, we implemented and modeled efficiency measures, tracked their impact on energy and water consumption, and demonstrated that resource efficiency can be achieved in small commercial buildings. Then after the the demonstration phase, we need to demonstrate those solutions, or I guess demonstrate those solutions and deploy them to a wider audience. We're currently in the final year of the grant, which is in the deployment phase. We've developed easy-to-use resources to assist building owners and operators to identify opportunities for improvement, determining their financial impact, energy and water efficiency calculators, and other toolkits for both new and existing buildings. So we've deployed a lot of resources, and here are some examples that you can find on our website. We've got a combustion appliance safety guide. We have a toolkit for dealing with campuses with multiple buildings, a toolkit for recreation centers, a toolkit for fire stations, and several different tools for calculating HVAC energy and envelope savings. Small commercial building operators are often unaware of the benefits of energy efficiency, or they are skeptical that the savings from energy efficiency projects will materialize. Small commercial building assessment tools and protocols to identify and analyze energy efficiency measures. Building operators need better feedback on how buildings and systems are performing in order to manage energy effectively. Lack of training around best practices for energy efficiency causes small commercial building operators to overlook opportunities to improve building efficiency through operational adjustments and equipment upgrades. If small commercial buildings identify suitable measures, they still face the issue of how to pay for the project. Small commercial buildings have less available capital and lower credit quality, which limits access to financing. All of these barriers combined make the small commercial building sector challenging for energy efficiency, but energy efficiency can be attained. So what is benchmarking? Benchmarking is the first step in improving building energy performance. Energy usage cannot be effectively managed until it is measured and evaluated. Benchmarking is used to evaluate building performance by comparing one building against its peers. So, for example, you can compare the energy use intensity of one building against the national median. You can also compare the energy use intensity for one recreation center against other recreation centers in your portfolio, or those in other cities' portfolios. You can also use benchmarking to compare the same facility to see how it's changed over time. Benchmarking can be used for prioritized upgrade efforts. It can also be used to set energy reduction goals and track progress. Benchmarking helps to evaluate savings for implemented measures, and it may also help to meet city benchmarking requirements your city has a benchmarking ordinance. Another side benefit of benchmarking, at least in a municipal portfolio, is that you can help to identify and cease payment for unused meters. The barriers to benchmarking for recreation centers here in Atlanta. We've had issues with documentation, the staff time and burden, identifying hundreds of decades old utility meters, and also in collecting records for building floor area. Another barrier just in the process is the difficulty to obtain building documentation and utility account information, and lack of a process for verifying data. Staff training and budget limitations and technical experience in energy efficiency and issues with staff turnover are also challenges. I guess we ran into a lot of missing and estimated utility data. We've also ran into issues where utility management systems aggregate data from multiple meters at the same address. Finally, and I guess this doesn't impede benchmarking, but it impedes your ability to make use of it is that the data for most of the buildings in the city's portfolio it's only updated once per year. There's a lag between when it's input and when the energy consumption actually occurred. So some of the lessons learned, you can't always depend on records of building floor area. You really need to have building plans, and plans aren't available to measure the actual building. Also, depending on aggregated billing information may not provide an accurate picture of utilities. Verifying utility account information and retrieving data directly from the utility company can help to avoid issues with aggregated meters. Some best practices for benchmarking. It may be worth considering using an automated utility data input service to ensure accurate and timely utility bill entry. Depending on a person, you inevitably end up waiting quite a long time to get the data, and then it may not be accurate. Benchmarking data needs to be accessible by recreation center managers and facility management staff in order to be useful. Benchmarking data can also be used to evaluate the savings from implemented measures. It's also good to update building use details such as occupancy and operating hours to ensure that you're getting accurate benchmarking. So recreation centers are a unique building type. Across the nation, there are approximately 26,000 municipally owned recreation centers and many more recreation centers that are managed by nonprofit organizations or other businesses. The majority of recreation centers are smaller than 50,000 square feet. The Department of Parks and Recreation of Atlanta manages 28 recreation centers, along with many other park and recreation facilities. Recreation centers offer a range of fitness and education activities, including recreational and league sports, weight training and fitness, aquatics, after-school programs, senior arts and crafts, and much more. The typical recreation center has a gymnasium, a workout area, an activity area, offices, classrooms, rooms, and a computer lounge. Other interior spaces at some recreation centers include an indoor pool, a stage, and a theater. Exterior amenities include an outdoor pool, athletic field, tennis courts, playgrounds, and parks. Through the ACBI grant, Southface performed energy and water assessments for 6 City of Atlanta recreation centers. City of Atlanta is also updating its facilities through the Renew Atlanta Bond Fund, and they're performing investment-grade audits and upgrades for many of their recreation centers. So looking at the performance of City of Atlanta's recreation centers, you see that there's a wide range of performance. 16 recreation centers were benchmarked with Energy Star Portfolio Manager and compared against each other and the national median fitness center, health club, gym, property type. The median fitness center is represented by the dashed line. The 6 recreation centers that received an assessment are shown in green. The national median site EUI is about 69.3 kBTUs per square foot. The median source EUI is 123.1. For reference, an office building has a typical office building has a median site EUI of 54 kBTUs per square foot and a median source EUI of 167 kBTUs per square foot. So a recreation center consumes a bit less than an office building. The median source EUI for City of Atlanta recreation centers is 124.8, pretty much identical to the national median. However, there's significant variation. Half of the recreation centers in this portfolio are performing worse than the national median, and half are performing better. This disparity in building performance is caused by a variety of factors. The indoor and outdoor pools, exterior lighting, differences in operating hours, and just differences in building use. The presence of an indoor pool significantly increases energy use. The recreation center with the highest DUI, shown on the left, has a source energy use intensity of 737 kBTUs per square foot. And this recreation center is a natatorium, which is a building that contains an indoor pool. The natatorium alone accounts for 42% of the annual source energy consumption for this portfolio of 16 recreation centers. And if you look at the other recreation centers that received an assessment, you'll see that they're spread across a different range of performance levels. We've got the worst performing recreation center, some that are right along in the middle, and 2 that perform better than the national median. The recreation center that performed the best on the far right had high efficiency air conditioning equipment, which contributes to the high performance. So the 6 City of Atlanta recreation centers underwent energy and water assessments using the Small Commercial Energy and Water Assessment Toolkit developed through the ACBI grant. The first step in doing the assessments was to do benchmarking. The City of Atlanta benchmarked the facilities, but the data needed to be verified and validated before we could proceed. So the Energy and Water Assessment Toolkit uses data downloaded directly from the Portfolio Manager to start the assessment. The next phase was to collect and analyze historical energy use based on that data that was downloaded. We also collected building drawings and other documentation. Then we conducted a site visit, interviewing the recreation center manager to discuss schedules, typical occupancy, activities that took place in the recreation center, known comfort issues or equipment malfunctions, and to study and evaluate the facility's existing system conditions and to identify practical efficiency and conservation projects. We then took a tour of the facility and then did a detailed inventory of the equipment, along with photographs of any issues. After completing the site visit, we recorded and integrated all the site visit notes, pictures, and project ideas, and developed a preliminary project list. Next, we went through the analysis. So we performed an engineering and economic analysis of the identified projects. Then we prepared a report and a presentation to City of Atlanta and staff. So based on the assessments that were performed on these 6 recreation centers, these are the energy use breakouts. The energy use shown in these charts is source energy. The 5 recreation centers that did not have a natatorium are shown on the left. Recreation center with a natatorium is shown on the right. You can see on a typical recreation center without a natatorium, heating is the highest end use, followed by cooling. So heating and cooling represent about 2/3 of building energy use. And lighting represents about 20%. Plug loads represented around 11% of annual energy use, and water heating, even in facilities that had an outdoor pool and shower facilities, was very low at only 3%. In the recreation center that had a natatorium, the energy use breakout is far different. Pool heating is the largest consumer of energy in a natatorium. The other end uses are more approximate. The processes that take place in an indoor pool are very complex due to evaporation, dehumidification, large amounts of outside air, and other factors. In a natatorium, lighting is actually one of the lowest end uses at only 8%. It may help that this facility had upgraded a lot of their high bay lighting to LED. So here are some of the low-cost measures that were identified in the energy assessments. The first is, I guess these 5 low-cost measures account for about 0.5% of the energy savings, but they have a combined payback of 1.3 years. The first measure was lighting controlled commissioning. So some of the recreation centers had motion sensor switches, but they didn't really seem to function. Commissioning of existing interior lighting controls can provide savings with little time and effort. The next measure is low faucets and shower heads. The City of Atlanta has the highest combined water and sewer rates of any city in the country. So replacing water fixtures makes a lot of sense. Many of the shower heads and faucet aerators are already low flow, but upgrading the remaining fixtures can reduce water consumption and water heating energy. Many of the computer labs are found to have computers that never shut down. Operational changes or network-wide computer power management software can ensure that computers are shut down when rec centers are vacant. Some other potential measures that are low cost that weren't included in the assessment are repair and replace faulty photocells for exterior lighting. This was a common issue seen in most of the recreation centers. So low flow faucet aerators and shower heads are a really easy way to save both energy and water. In faucets that are used for mainly hand washing in lavatories, replacing existing aerators with 0.5 gallon per minute aerators is a really cost-effective and easy retrofit. Size and functionality, and they're inexpensive. Also in facilities with showers, replacing the existing shower heads with WaterSense labeled 1.5 GPM shower heads can produce good shower performance and save water and energy. Many of the recreation centers had high efficiency condensing gas-fired water heaters. Water usage was also very low. However, on water heaters that had a recirculation pump, they didn't have timer switches. Installing a timer switch for hot water recirculation pump can reduce hot water or water heating energy by reducing the amount of heat loss through the recirculation loop. The majority of the savings identified in the recreation center assessment come from only 4 measures. These measures combined produce 19% energy savings with a simple payback of 4.5 years. Focusing on just lighting, HVAC controls, and pool measures may produce 20% savings in some recreation center portfolios. LED lighting and controls produce the highest savings, with 7.9% of annual energy use. And they reduce costs by 11.1%. Additional cost savings are likely to occur due to reductions in maintenance-related costs. Lighting rebates are also typically available, making these retrofits even more cost-effective. So 1 out of the 6 recreation centers had an indoor pool, and 2 out of the 6 had an outdoor pool. Due to this extremely high energy use of facilities with an indoor pool, the pool measures have a large impact on portfolio-wide energy consumption. For the one natatorium, installing a thermal blanket while the pool is not in use can produce 5.7% energy savings with a 1.3-year payback. Another common issue found in recreation centers and also in most small commercial buildings is programmable thermostats that are set to hold. By implementing thermostat setbacks using web-based thermostats or reprogramming the existing thermostats, you can produce about 3.5% savings. Installing web-based thermostats would produce a simple payback of about 2.2 years. Finally, on the natatorium, installing full pump controls to shut down the full pump whenever the pool is not being used can save about 2.1%. We'll get into some of the restrictions and additional regulations later. Existing lighting summary. This is a summary of all of the all of the lighting that was surveyed in the Recreation Center assessments. The vast majority of the lighting is T8. It consumed the largest amount of the annual electricity. The next highest consumer of electricity was HID, so metal halide and sodium vapor fixtures. The majority of these fixtures are located outside. So there were some metal halide fixtures located indoors. LED lighting installed in the natatorium actually consumed the third most electricity. Even though it's really efficient, there was quite a lot of LED lighting. There's still T12 lighting remaining in 5 out of the 6 recreation centers. Replacing T12 lighting can produce a good payback. CFL fixtures weren't common in recreation centers. Most of the CFL fixtures were 2x2 troffers that had CFL lamps. These fixtures actually had a fairly high power consumption of about 80 watts per fixture. T5 lighting was found in some of the high bay lighting in gymnasiums that had been retrofitted. Incandescent fixtures were also uncommon, but there were some found. The lighting accounts for about 20% of the annual energy consumed in a recreation center. Light-emitting diode lighting, LED, is quickly becoming an affordable lighting solution with superior efficiency, light quality, controllability, equipment life, and environmental footprint. Retrofitting or replacing lighting fixtures with LED is one of the most cost-effective ways to reduce energy consumption and electricity costs. LED provides significant energy savings over incandescent, metal halide, and fluorescent technologies. LED has a long operating life, which reduces maintenance burden for facility staff. Lighting or interior lighting energy consumption usually occurs coincident with peak demand. Lighting energy also reduces the cooling load for a building, which produces additional savings. Due to the reductions in both cooling and lighting energy and demand savings, interior lighting retrofits have a high cost savings. LED also provides the benefit that there's no warm-up time required, unlike metal halide. LED fixtures also provide great controllability, with full range dimming available in LED fixtures. The best practices for LED upgrade projects. Purchase LED products that are certified by Energy Star, Design Lights Consortium, or Lighting Design Labs. Always test LED upgrades for a few fixtures at your recreation center before ordering a large quantity of fixtures. Ensure that the upgraded fixtures deliver the appropriate illumination levels, foot candles. You basically don't want it to be too bright or too dim. One-for-one fixture replacements or lamp-for-lamp replacements may not provide appropriate illumination. Also, combining LED retrofits with occupancy and vacancy controls for rooms with intermittent occupancy can maximize energy savings. Also, be sure to apply for utility rebates to reduce payback. So 4 out of the 6 recreation centers had already upgraded high-bay metal halide lighting to T5 or T8. 1 recreation center had converted high-bay lighting to LED. The remaining 1 recreation center had T12 high-bay lighting. High-bay fluorescent lighting requires no warm-up time and is far more efficient than metal halide. However, fluorescent lighting has poor dimming capability, shorter lamp life than LED, and higher energy use. So this is a Boys and Girls Club that received an LED lighting upgrade. Replacing high bay metal halide fixtures in gymnasiums and high bay spaces with LED fixtures can reduce lighting power by 55%, while eliminating maintenance calls for lamp replacement. There is no warm-up time required, so lights come on instantly, and they work great with motion sensor controls. Adding dimming capabilities to gymnasiums also allows for greater flexibility of space use, since you can use dimming for events, movies, and other functions. LED fixtures are fully dimmable and pair well with photosensor controls for daylight harvesting applications. If you have natural daylight coming into your gymnasium, LED fixtures with daylighting controls can save a lot of energy. So in this project, 400-watt metal halide fixtures were converted to 240-watt LED fixtures, along with dimming controls and occupancy sensor controls. If you still have incandescent lamps in your recreation centers, replace them with LED lamps. You can also replace CFL, screw-in CFL lamps with LED. The most common type of fixture in recreation centers is T8. T12 and T5 were also found. Even though T8 lighting is fairly efficient, converting it to LED can still produce big savings. Converting fluorescent fixtures to LED can produce savings of more than 40% with a 6-year payback. There are 3 different options for upgrading existing linear fluorescent fixtures to LED. The first option is an entirely new LED tropper. A new LED fixture provides excellent efficiency, full dimming, long lifespan, and it looks great. However, this is the most expensive upgrade option, typically more than $250 per fixture. Consider using a new LED tropper if dimming and daylighting controls are required. It also may make sense when moving from a T12 to LED. Option 2 is to use a door retrofit kit, similar to the picture on the left. The advantages of a door retrofit kit are that it has similar efficiency and lifespan as a new LED fixture. It also looks similar to a new LED fixture. Dimming may be available, but it's usually not quite as good. Existing fixture housing is retained, making installation easy and minimizing disruption. A door retrofit kit has medium installation costs, typically about $165 per fixture, which results in better payback than replacing the entire fixture. The third option for upgrading linear fluorescent fixtures to LED is to use LED retrofit tubes. LED retrofit tubes provide good savings, but there are some compromises. Generally, LED retrofit tubes don't provide dimming. They don't have quite as long of a lifespan, and they really don't offer any improvement in aesthetics. They look pretty much exactly like the fluorescent lamps that they replace. It's recommended that you install plug-and-play LED lamps that don't require bypassing the ballast for safety reasons. The plug-and-play installation makes this a really easy retrofit with some of the lowest installation costs. Somewhere around $20 per lamp, although you may see lamps as low as $13 a piece. If you don't have to replace the ballast, this provides a really good payback. Even if you have to replace the ballast, the full project is still usually the most cost-effective. Combining lighting retrofits with lighting controls can maximize savings. When installing motion sensor switches, they have two operating modes. The first mode is vacancy mode. This requires a manual on and automatic off. A vacancy mode produces the most savings. It's appropriate for offices and classrooms, especially whenever they're adjacent to a corridor. It basically reduces false triggers so that lights aren't coming on and off whenever the room is not occupied. The second mode, and this is the default mode for most controls, is occupancy mode. This is automatic on and automatic off. And it's great for convenience, but you may get some false triggers. Exterior lighting, retrofitting exterior lighting with LED can also provide big savings. Rec centers have an extensive amount of exterior lighting. Replacing metal halide wall packs and pole lights with LED fixtures with integrated controls can produce big savings, especially if you install fixtures with integrated photocells and bi-level occupancy controls. These fixtures will automatically dim whenever no one is near it, and then they'll brighten up whenever occupancy is detected, providing both energy savings while also providing security and illumination. And this graph was from some of the energy monitoring at a Boys and Girls Club, something like 88% reduction in lighting energy per night. With an indoor pool, energy use is typically very high. Pool evaporation is a significant driver of natatorium energy use and water use. Water is constantly evaporating from the surface of the pool, simultaneously removing water and thermal energy from the pool while adding humidity from the air. Humidity in the air is removed using energy-intensive mechanical processes. The natatorium that was surveyed has 2 pools maintained above 86 degrees with a combined surface area of 8,700 square feet. The air is maintained at about 81 degrees with a relative humidity of 60%. In these conditions, the average evaporative losses are about 50 gallons per hour. And water, whenever it evaporates, absorbs a lot of heat, roughly 8,000 BTUs per gallon. The resulting heat loss to evaporation is around 400,000 BTUs of heat every hour. About 4 therms, although it's not all coming from gas. The water in the air must then be removed by the dehumidification unit. So it requires a lot of additional energy. But some of that energy is covered to heat the pool water. So in this natatorium, about 438,000 gallons of water are lost to the atmosphere and must be made up in municipal water. That municipal water has to then be heated to the pool temperature, requiring even more energy. Maintaining pool water that is not too cold for bathers while maintaining air that's not too humid results in a large amount of energy and water consumption. One simple strategy that can reduce evaporation and resulting energy consumption is to install a thermal blanket when the pool is not in use. A thermal blanket is essentially a vapor barrier that is used as an impermeable pool cover. Covering the surface of the pool with a thermal blanket can reduce energy and water consumption by more than 30%. The cost savings for installing a thermal blanket at this natatorium are more than $13,000 per year. $13,000 for a piece of plastic. Pool covers are required by the Energy Code, ASHRAE 90.1. The energy and water and cost savings are huge. However, a study by USA Swimming estimates that only 5% of natatoriums use the thermal blanket. So this issue is pretty widespread. The best way to reap the energy savings from installing a thermal blanket is to purchase a retractable thermal blanket that can be wound onto the storage reel. This type of pool cover is designed to be deployed and retracted quickly on a daily basis. This pool cover can be rolled onto the spool and stored in a convenient location. Typical cost for a pool blanket and storage reel are about $1.65 per square foot. Source energy savings may exceed 200 kBTUs per square foot of pool surface area, and the payback is often less than 1.5 years. In addition to energy savings, pool blankets reduce water use, reduce pool treatment chemicals, and improve indoor air quality. and prolong equipment life. This measure requires a small amount of capital, but it also requires a large amount of staff training and monitoring to ensure that the thermal blanket is deployed on a daily basis. So installing a thermal blanket with a storage pool, you need to deploy it after the pool is closed and then retract it by rolling it onto this spool whenever the pool opens. So pool energy consumption, or pool pumps, account for about 12% of natatorium energy consumption. The pool water must be filtered to remove particles and distribute treatment chemicals. Health codes typically require pool water to be turned over once every 6 hours. But the Energy Code, ASHRAE 90.1, requires pool pump timer control, unless required by a local health code. In Georgia, you can install a timing device as long as the water is turned over one time immediately prior to the pool reopening. Pools are typically closed for 12 hours per day, which allows the pump to shut off or slow down. Timer controls can reduce pool operations by about 6 hours per day, saving 25% on energy use. Installing a variable frequency drive and timer controls can allow maximum energy saving so that you can slow down the pump and then speed it back up, never turning it completely off. The HVAC equipment in most of the recreation centers is unitary equipment, so split systems and package units, mostly with gas heat. Roughly 2/3 of the energy consumed at recreation centers is used for heating, cooling, and ventilation. Like most small commercial buildings, these were heated with unitary units. Most of the systems surveyed were less than 10 years old and in good condition. One exception is the photo in the top left showing some extensive hail damage. Most of the systems had gas heat with 80% furnaces. Cooling efficiency for most of these units was near the code minimum, though one building had 15 SEER equipment. These HVAC systems are controlled with programmable thermostats that can be programmed to maintain different temperature set points at scheduled times. Small adjustments to the thermostat set point can result in large reductions in HVAC energy use. Resetting the thermostat while a building is not occupied, referred to as a thermostat, and setting back the thermostat, produces no comfort complaints while saving energy, reducing equipment repair. While programmable thermostats can be used to implement thermostat setbacks, few recreation centers actually utilize the programming feature and instead hold a constant set point temperature. This issue is not unique to recreation centers. Nearly all small commercial buildings have thermostat schedules that are not optimized for maximum efficiency. Wired thermostats in small commercial buildings usually set to hold instead of running a program. Programmable thermostats often have unintuitive interfaces for adjusting temperature set points and schedules. To make matters worse, most buildings have multiple different types of programmable thermostats, each with its own interface. Comfort issues and differences in the perception of thermal comfort lead to frequent set point adjustments. Frequent adjustments by uninformed occupants using unintuitive devices lead to poor thermostat programming, abandoning the scheduling capabilities altogether. Finally, facility management staff are stretched thin, putting out fires, unclogging toilets, and resolving complaints at dozens of different sites. The last thing they want to have to do is drive to a rec center to change the set point on the thermostat because someone is uncomfortable. So how do you implement thermostat setbacks without generating extra work for your facility management staff? How do you ensure that the programming changes actually stick? The answer that we found in our work with small commercial buildings is to install web-based thermostats. Installing web-based thermostats allows you to implement setbacks while also taking advantage of other advanced features. It's recommended that you install internet accessible thermostats or web-based thermostats for systems that have, or rec centers that have unitary equipment. Enable the smart recovery or optimal start feature such that the system start time is determined algorithmically so that the building reaches set point by the scheduled occupied time. Setting up schedules that match the operating schedule of the building, and setting temperature set points during unoccupied periods can produce big savings. Setting the thermostat back to 60 degrees during heating mode or 85 degrees during cooling mode is recommended. Web-based thermostats also provide a feature where you can set the occupant adjustment range and lock out the device with a passcode. Occupants are able to alter the set point by a predetermined amount, but they can't go beyond it. You can also allow occupants to set a hold duration so that occupants can turn on heating and cooling after hours for a limited period of time. Internet-accessible thermostats provide remote management. You can adjust schedules and set points as necessary from any location with any device that has an internet connection. You can also do event scheduling, so you can override the default schedule and set points for holidays, rentals, and other events that are known in advance. You can also configure alerts. Internet-accessible thermostats facilitate energy-efficient HVAC management strategies while also improving facility management capabilities. But central accountability and oversight are required to maximize savings. Periodic reviews of thermostat schedules and HVAC equipment runtimes are required to ensure that savings persist. You can see from this that you get some pretty slick graphs. You can also use the motion sensors to do automatic setbacks or adjustments. So this is a summary of all the measures that were recommended for recreation centers. The largest savings are from the LED lighting, the pool blanket was second. A few of the measures in this that weren't included in the low-cost measures, the high-impact measures, are replacing the water heater. There was, I think, one water heater that wasn't a condensing water heater. Also replacing some of the older refrigeration equipment with Energy Star labeled equipment can produce some good savings, but the payback's a bit longer. Implementing this whole package of measures produces about 20% savings with a 4.5-year payback, and it saves about $71,000 per year. The total cost is a little over $300,000. So here are some resources for improving the efficiency of your recreation centers. The first resource is the ACI tools located at the top. There are calculators, toolkits, case studies, and a lot of other different tools for improving efficiency. The second resource is the nonprofit Energy and Water Efficiency Initiative case studies. So these are boys and girls clubs that are very similar to recreation centers that received energy and water efficiency upgrades. Many of these projects are similar to those that were discussed in this webinar. And by implementing these projects, this team of boys and girls clubs was able to achieve second in the EPA's National Building Competition for energy savings. They placed first for water savings. So these measures definitely work. My contact information